Welcome back to this next video in which we are discussing groups of order 12. Okay, so we're now in the process of trying to prove that if we have a group of order 12 with 4 sylow-free subgroups, then it is isomorphic to the alternating group on the set of 4 elements. Now, what we've so far succeeded on doing is creating this group action where we have the group capital G here of order 12 acting on the set of sylow-free subgroups here. And the reason this is such a good idea to create this is that, look, we are now associating with all the elements of the group a set permutation of a set which contains 4 elements. Remember, that's what a group action does. It gives it or associates to every element of a group a set permutation of the set on which the group is acting. Okay, now there's a way of making this very explicit, which is through devising permutation representations, and that's what we're going to do now. Okay, right, so what we can do is we can use this group action to create a permutation representation, which, remember, is a group homomorphism from the group capital G, okay, the group that's acting on the set, onto the symmetric group on that set, or the symmetric group on that set that the group is acting. Okay, and the set that the group is acting is effectively just a set of 4 elements, okay? Forget that we've called them H1, H2, H3, H4. It might as well just be an arbitrary set of 4 elements. So we're actually going to map the elements of our group onto the elements of the symmetric group on the set of 4 elements. Okay, so this homomorphism here is called a permutation representation, and from any group action it's possible to devise one of these, and from any permutation representation it's possible to devise a group action. They're just 2 different ways of viewing the same thing. This one, if you like, is more explicit. It is explicitly saying, let's associate with every single element of the group a set permutation of the set, whereas a group action is slightly less explicit, but they have the exact same information encoded within them. And the reason that this mapping will be a group homomorphism is because of axiom number 1 of a group action, the compatibility of the group action with the composition law of the group. Okay, so just to make this utterly explicit, the way that this will work is it will take any element, little g, of the group, capital G here, and of course little g sends each one of these elements of the set onto the element that's underneath it in the row. So H1 will be sent onto what's in this box, H2 will be sent onto what's in this box, H3 will be sent onto what's in this box, and we will now associate with this element G. That's what the permutation representation is going to do. It will associate with this element little g, it will map it onto the element in S4 that is that equivalent set permutation here. Okay, and that will end up being a group homomorphism, and if you want further explanation for that, go back and watch the videos on group actions earlier on in this playlist on group theory. Okay, so from the group action then we can devise this permutation representation where we're now going to have this group homomorphism which will send elements of the group onto elements of S4. Okay, so obviously what we want to do is try and twiddle around with this, tinker around with this a little bit, and reduce it into an isomorphism from the group capital G onto A4, or show that indeed that's what it's going to be. Okay, so the first thing I want to do is show that this is actually going to be an injective group homomorphism, because that's the complexity that often people forget with group actions, that we don't know that this isn't non-injective. Okay, and what I mean by that is that this group action might associate to different elements of the group the same permutation of the set of 4 elements here. So you might have 2 different elements of the group, G1 and G2 here, let's say. So here's G2. And their rows might be identical to one another, i.e. they might send these 4 sylow-free subgroups onto the exact same things as each other. Okay, and in that case, when we come to the permutation representation here, they'll be sent onto the same element in S4, they'll be associated with the same permutation of the set of 4 elements. Okay, what I want to prove is that that's not the case for this group action. Okay, I want to prove that the permutation representation is an injective group homomorphism for my group action. And there's a special word that people use to describe such group actions. We call them faithful group actions. So if every single element of the group is associated with a unique set permutation of the set on which the group is acting, then we call the group action a faithful group action, and it just means that the permutation representation associated with that group action is going to be an injective group homomorphism. Okay, so how can we prove that? Well, what we need to prove is that the kernel of the group action, which is just the kernel of the permutation representation here, this group homomorphism, is just equal to the trivial subgroup. Okay, i.e. only contains the identity element. Now, how am I going to do that? How can I prove that for this group action, the kernel of it is just the trivial element, the identity element? Only the identity element is associated with the identity permutation, basically. Okay, well, why can there not be any other elements that are associated with the identity permutation? Well, suppose there was another element in here apart from the identity element that was associated with the identity permutation on the set of 4 elements. That element would have to be in all of the normalizers of each of the HIs in G, because it would have to fix every single one of them. So if there was some little g is an element of the kernel of the group homomorphism, or rather of the group action, that was not equal to the identity element, then little g would have to be in all of the normalizers. So g would be an element of the normalizer of every single one, because it would have to fix every single one if it's going to correspond to the identity permutation. So if I draw this on the page, what we're trying to argue is that there cannot exist a little g that is not equal to the identity which sends every single one of these, and I'll just make sure this is in view, good, onto themselves. So h1 sent onto h1, h2 is sent onto h2, h3 onto h3, h4 onto h4. Okay, I want to prove that this cannot exist, okay, so I'll draw a cross for it. Okay, so how can I do that? Well, if it was the case that this was true, that this existed, then it would be in the normalizer of every single one of them. But now we use the lemma that I've come up with. The normalizer of every single one of these is just equal to every single one of these. So the normalizer of hi and g is just equal to hi. So this is equivalent to saying that g would have to be in all of the hi's. Now, why is that not possible? Well, because of the comment that we made right at the start. When we started this, all of them intersect just with the trivial subgroup. They have the only element that's common to all of them is the identity element. Okay, all of the non-identity elements are not common between them. So there is going to be no element, little g, that is not equal to the identity element that is in all of these sylow-free subgroups, and therefore there cannot be an element which is in the kernel of this other than the identity element. Okay, so that's how you can disprove that using this lemma. That's why I did the lemma, so that we could prove that this was a faithful group action. Okay, so overall what we can now conclude is that the kernel of the group action is the trivial subgroup, i.e. only the identity element is going to fix every single one of the elements, capital H1, capital H2, capital H3, and capital H4. All of the other elements are not. Okay, so that means now that this is truly an injective group homomorphism, and that all of the elements of the group are going to be associated with distinct elements in S4, i.e. that this is going to be an isomorphism onto a subgroup of S4. Of course, it's not going to be an isomorphism onto S4, but if we limit S4 now down to just the image of this, then it will become a surjective group homomorphism, and since it's injective and surjective and a group homomorphism, it will then be an isomorphism. Okay, what we obviously now need to prove is that the image of this group homomorphism is indeed equal to the alternating group on the set of 4 elements. Okay, so how am I going to do that? Well, we're going to have to go back and study G in a little bit more detail, and remember that this is a group homomorphism, an injective group homomorphism, and therefore our isomorphism onto a subgroup here, i.e. if I change the symbols here, the elements here are truly the same as a subgroup here. The algebraic structure is the same. Now, okay, we know that G contains all of these subgroups, capital H1, capital H2, capital H3, capital H4, all of these sylow-free subgroups, these 4 sylow-free subgroups. Now remember, all of these have very simple structure. They'll contain an identity element and then 2 elements of order 3. Okay, so overall, how many elements of order 3 must G contain? G must have 8 elements of order 3 at least. Okay, so 8 elements of order 3. And in fact that will be all of the elements of order 3, because if there was another one, then that would also generate a sylow free subgroup. So just 8 elements of order 3. So G must have 8 elements of order 3, and I'll remind you again of how I concluded that. All of these sylow free subgroups here, their only common element is the identity element. Okay, their other elements are both going to be of order 3. So this one will have 2 elements of order 3 and the identity. This one will have 2 elements of order 3 and the identity. This one will have 2 elements of order 3 and the identity, etc. Okay, so all of them have 2 elements of order 3 that are all different from the elements that the others have of order 3. Okay, so overall that means that we must have 2 times 4 elements of order 3, i.e. 8 elements of order 3. Okay, right. Now, because this is an isomorphism from the group onto a subgroup of the symmetric group on the set of 4 elements, okay, then an element of order 3 here is going to correspond to an element of order 3 here. Okay, so phi of G, the image of G under this injective group homomorphism here, must contain 8 elements of order 3. Okay, so 8 elements of order 3. We know that the alternating group on the set of 4 elements is going to contain 8 elements of order 3. We saw them all. Okay, I'll just remind you of them. All of these elements where we have a 3 cycle with a 1 cycle, they are all of order 3. If you compose them with themselves 3 times, you'll get back the identity element. So all 8 of these are of order 3. Okay, so now what I can do, and in fact those are the only elements in S4 of order 3, that's another important point. Okay, only those elements that contain the 3 cycles are of order 3. Okay, hence this image of the group under the group injective group homomorphism here, if I intersect it with the alternating group on the set of 4 elements, this intersection must contain all of these 8 elements of order 3 that we've got listed over on the other page. Okay, so understand those are the only elements in the symmetric group on the set of 3 elements. Sorry, the symmetric group on the set of 4 elements that are of order 3. Remember the elements that I haven't drawn out. Okay, so I'll just give you a bit of a better argument for that. So in S4 we have the identity element, we have all of these 3 cycles with 1 cycles, we have the double transpositions, and then the things that we haven't shown, the elements of the odd elements, those are going to be the transpositions, the single transpositions. You'll have 6 single transpositions and then 6 4 cycles. Okay, 4 cycles are obviously going to have order 4. Transpositions are going to have order 2. Okay, the double transpositions will have order 2. So these are the only elements of order 3. Okay, hence, if we intersect the image of this injective group homomorphism with A4, it must share all of those 8 elements. It must also share the identity element. Okay, so we've already concluded that 9 of the elements between these two are shared. I want to conclude that actually all of the elements are shared. This is equal to A4. And of course we know the order of the image of this homomorphism is going to be order 12. Okay, because it's an injective group homomorphism, you've got 12 things over here, so in the image you're also going to have 12, and hence this is equal to A4. Okay, so why can I do that? Well, of course I just apply the Granger's theorem. This intersection has to be a subgroup of both of the things that you've intersected here. Okay, so it will have to be a subgroup of A4. A4 has order 12. We're saying that this has to this intersection has to contain at least 9 elements. The only option now is that it's the subgroup that's the improper subgroup of A4, i.e. that this intersection is A4. Okay, you can't have a subgroup that shares 9 elements that isn't the improper subgroup. Okay, so it has to be A4. So when I intersect these two together, it has to be A4. The order of this is 12, the order of this is 12, hence I can conclude that phi of G, the image of this homomorphism, is A4. Now what I can do is reduce my group homomorphism down here, reduce the size of the codomain down to A4, okay, and I will now have an injective surjective group homomorphism, otherwise known as an isomorphism. So I have devised here an isomorphism from my group capital G to A4, hence I have shown you that G is isomorphic to the alternating group on the set of 4 elements. So truly, there is your argument as to why, if you have a group of order 12 with these 4 sylow-free subgroups, you can show that the group is isomorphic to the alternating group on the set of 4 elements. Okay, so theorem 1 is proven. What I just want to do now is make a closing remark. Okay, so my closing remark is that if you have a group of order 12, okay, so we've got some group of order 12 here, and this closing remark is going to be important in the next video in the playlist on group theory, which will be entitled groups of order p squared q. Okay, if I've got some group of order 12 here, either it has a normal sylow-free subgroup, so by theorem 1, either it has a normal sylow-free subgroup because it only has one sylow-free subgroup, hence that will be a normal sylow-free subgroup, or it's isomorphic to A4, but I claim A4 has a normal sylow-2 subgroup. I claim it only has one sylow-2 subgroup. Now remember, 12 is equal to 3 times 2 squared. So you only have sylow-free subgroups and sylow-2 subgroups. Sylow-2 subgroups, don't get confused by the name, they'll be of order 4. They're called the prime, but of course they'll be size, the prime to its highest power. And in the case of 2, that's 2 squared, which is 4. Okay, so I claim that the alternating group on the set of 4 elements actually has only one sylow-2 subgroup, i.e. only one subgroup of order 4, okay, which will therefore be normal. So even though it doesn't have a normal sylow-free subgroup, it will have a normal sylow-2 subgroup. So what you can therefore conclude is that any group of order 12 will have a normal sylow subgroup. Either it will have a normal sylow-free subgroup, option 1, or it will be isomorphic to A4, in which case it will have a normal sylow-2 subgroup. So it will have a normal sylow subgroup, that is the important thing here. Okay, so how can I prove that there's only one sylow-2 subgroup? Well, why is there only one subgroup of order 4? Well, the only subgroup of order 4 is the subgroup that you can get by putting the identity element in with all 4 of the double transpositions here. Okay, if you put those together, the identity with the double transpositions here, you end up with a subgroup. And that's the only subgroup that you can build of order 4. The first sylow theorem tells us that there must exist a sylow-2 subgroup in A4. Okay, so there must be a subgroup of order 4. You can't build it by putting in the 3 cycles here, because they have order 3, so they'll create a subgroup of order 3 inside that subgroup of order 4, okay, which contradicts Lagrange's theorem. So you can't have any of the 3 cycles in there. So the only things that you've got left to put in are the double transpositions, and you must put all 3 double transpositions in. So although, to me, it isn't instantly obvious that when you compose 2 double transpositions together you'll get another double transposition, or the identity, it must be the case because we're forced to that conclusion by the first sylow theorem and Lagrange's theorem. Okay, so you don't need to worry about, is it the case that if I compose 2 double transpositions together I always end up with another double transposition? It must be that way because I have to have a subgroup of size 4 by Sylow's first theorem. I cannot put in these elements of order 3 because, as I say, that will contradict Lagrange's theorem because they create subgroups of size 3 inside that subgroup of size 4, okay, which is a no-no. Therefore, there's only one option left, the identity with these 3 double transpositions, and that must be our one and only sylow-2 subgroup. Okay, so the closing remark then is if you've got a group of order 12, it will always have a normal sylow subgroup, either a normal sylow-free subgroup, or it'll be isomorphic to A4, which has a normal sylow-2 subgroup. And we'll use that fact in the next video entitled Groups of Order p squared q.